Hi everyone, I'm Nick, and today I'll be presenting my MSc Computer Science individual project on unsupervised deep loop closure detection with binary edge images. So what exactly is loop closure detection? In robotics, one of the most important things is for robots to attain positional awareness, so we want to know where exactly a robot is at any point of time. This is commonly used in applications such as, for example, Mars rovers or self-driving cars, and this problem is known as SLAM. And one common approach to solving SLAM is just to place a camera on top of the robot itself and allow this camera to capture a video. What we do with this video is we just compare adjacent images within this video and try to estimate the motion of camera. But the problem with these estimates is that they accumulate drift over time because we are only considering adjacent images within the video itself. So this brings in the solution of loop closure detection. We compare a newly captured image with all previous images captured in the video a distance away, and we can identify if this image match. If it's a match, that means we have revisited the same location and we can update our positional estimates of the robot itself. What then are binary edge images? Binary edge images are a reduced representation of an actual RGB image. And an RGB image is basically what we see commonly. It contains 3 channels, red, green, and blue, and each pixel within each channel has a intensity value ranging from 0 to 255. So it's like an unfiltered information here, as we can see here. A binary edge image, on the other hand, only contains one channel with 2 values. 1 where there's a white pixel, and 0 where there's a black pixel. So what exactly does a binary edge map capture from an original RGB image? So basically it shows where exactly the edges of the original RGB image occurs. So let's take this mirror for example. We could see that the edges of this mirror is in a white pixel in the binary edge map, whereas a wall which has no edges here is just captured as a black pixel. So binary edge maps basically contain much less information than an RGB image, but conversely, because it contains so much less information, it takes up less memory space. So what exactly is our research problem? So there's a group of researchers called Murai et al, and they designed this visual odometry system that has a very low power consumption and high frame rate. And the reason why their system has such low power consumption and high frame rate is because they use binary edge maps rather than RGB images to do visual odometry. And because binary edge maps have such smaller data transmission content, it becomes so much more efficient. So what we want to do is to figure out if using such binary edge maps, which are so much more reduced versus a RGB image, will we still be able to perform loop closure detection? Because if we are able to perform loop closure detection with this reduced set of image, we can basically extend the capabilities of this visual odometry system while still retaining its high efficiency. Before we move on to the methodology, we have to emphasize that there's the importance of low false positive in loop closure detection. What exactly is a false positive? A false positive occurs when 2 images are actually determined by the algorithm to be a match, when although in reality they are not of the same place. So false positives are very bad in the context of SLAM because they severely corrupt the positional estimates. Therefore, one of our main concerns is basically we want a low false positive rate in our loop closure detection algorithm. Now let's move on to how we actually solve the loop closure detection problem. Our loop closure detection algorithm consists of 2 steps. First is the compression phase and second is the matching phase. Why do we need a compression phase? Our input binary edge image are of size 256 by 256. So we have almost 65,000 values, each representing a pixel in the input image. What we want to do is to basically reduce the number of dimensions of this input to a smaller size representation of maybe 4096. So a sign of a good compression phase is that this 4096 smaller dimensional vector is supposed to be representative of the key features within the original main input binary edge image. The next step then in the matching phase is to match these smaller size vectors. So the main key objective within the matching phase is to reduce the amount of false positive loop closures, which, as we have mentioned, is very detrimental in the loop closure detection context. Let's talk about a few key features of our compression phase. The core of our compression phase is using this thing called an auto-encoder. An auto-encoder is basically a form of neural network that helps us identify the most important features of an input. So what we actually do during a training phase is that we actually put a binary edge image through an encoder to get a smaller dimensional vector. And because this vector is of a smaller dimension, we inevitably lose some information through the encoding phase itself. What we then do is to also try and recover the original image through a trained decoder. This will ensure that the smaller dimensional vector captures the most salient features of our input, such that it can reconstruct the input through the decoder despite losing some information in the encoder itself. So once we've trained both the encoder and decoder, we basically just toss away the decoder and use the trained encoder for future predictions. So by putting future binary edge maps through our trained encoder, we could get smaller dimensional vectors for each binary edge map. Let's call this smaller dimensional vectors latent space representation. Another thing that we use is this thing called variational autoencoder. And the reason we have to use this is because our latent representations are actually spaced quite far apart. And this is because of the extreme values of binary edge maps. Binary edge maps only contain a value of 0 and 1, and therefore they tend to look quite different from one another versus a typical RGB image, which contains value of 0 to 255 and tend to look a bit more similar. As a result, as we can see before we apply this variational autoencoder, these orange labels are actually belonging to the same image, but they are spaced quite far apart in terms of their latent representations. So what we actually do is that we regularize the latent space. What this means is that we actually apply some kind of restriction on the way the latent space is structured. In this case, we force the probability distribution of the latent space to follow a normal distribution, for those of you that know statistics. And because we do this, the gaps between the latent space representations are reduced. The last thing that we do is this thing called random homography deformations. And we do this so that our algorithm can be more robust against viewpoint changes. Viewpoint changes are basically when, for example, when a camera faces an image from two different directions, this image might look different, although the actual place is actually similar. So we want our algorithm to be robust against such situations. To do that, we actually apply random homography deformation. A homography deformation, as you can see below, is basically just kind of mimics a natural viewpoint change of a camera, which in this case is maybe taking this image from a bottom left angle instead. And what we actually do is that we use our autoencoder together with this, where we put this deformed image through the autoencoder to try and reconstruct the original image. And doing that allows our latent representation to be a bit more robust against viewpoint variations. So what happened after we get the latent representation of each of the images? The next step would be to just match this latent representation to figure out whether or not a loop closure has actually occurred. Remember that a key detail within this matching phase is that we aim to reduce the number of false positives, which, as we have mentioned, is very detrimental in the case of loop closure detection. So how do we go about matching each of these latent vectors? We basically plot the element of each of this vector in an n-dimensional space and calculate the Euclidean distance in between them. For aid of visualization, I've reduced the number of latent space to 2, although the number of dimensions of the actual latent space is much larger. So for each image, it actually has a value within this 2-dimensional space. So we just plot the image value within this 2-dimensional space for each image and just draw a line between them. So the length of this line is basically the Euclidean distance. So the longer the Euclidean distance, the further away the latent representation are. And this implies that our images are more different, and the converse is also true. So in order to get a similarity score, then we just basically use the inverse of the Euclidean distance. So using that, we are able to get a similarity score between an image and all other corresponding images in the test dataset. The last two steps then are rank reduction and adjusted Smith-Waterman. So let's talk about rank reduction first. So rank reduction aims to remove the common themes within the dataset using the technique of removing the largest eigenvalue, for those of you that know linear algebra. But technical details aside, let's just use an example to show what rank reduction does. So in this dataset, we have many images of walls, but these walls are all taken at different locations. So without rank reduction, the algorithm actually matches this to be of a similar location, although in actuality it is not. So what rank reduction does is that it basically reduces the similarity score across all images that actually contain these wall-like common themes, and therefore that actually reduces the number of false positive matches that we actually get from our algorithm itself. The final step then is just adjusted Smith-Waterman. What adjusted Smith-Waterman does is that we add a temporal constraint. What I mean by that is basically, rather than looking for individual image match, we look for a sequence of image matches. So individual image matches are more prone to error, as a wrong image match, a wrong single image match would basically lead to a faulty loop closure detection. So what adjusted Smith-Waterman does, as shown from this example here, is that rather than just matching image 1 and image 2, we also need to ensure that the next n image that follows after image 1 and the next n image that follows after image 2 also matches. And if this entire sequence matches, we can then determine a loop closure. And that will basically drastically reduce the number of false positive loop closure that our algorithm detects. So now let's move on to the actual results of our algorithm itself. So the first dataset that we tested on is basically the new college dataset. And here I've plotted the approximate trajectory. The blue lines in this image basically represents the movement of the robot itself. And the red dots and the green line in between basically represent two images and a detected loop closure between these two images. So as you can see, we are able to identify all of the locations where the blue lines overlap. Our image is also very similar to the actual truth labeled approximate trajectory provided by the dataset itself. Here are also some of the image matches that we have identified, and all of these image matches are actually correct image matches. So we are able to actually identify all of the unique loop closure sequences on this dataset with no false positives detected. Another dataset that we tested on is the city center dataset, and while we were not able to identify this particular set of loop closure sequences here, we were able to identify most of the unique loop closure sequences with no false positive results. And again, here are some of the example image pairs that our algorithm has identified as well, which are all matching. The last thing that we actually tested on is the outputs of the Scan5 device. So the Scan5 device is basically what I talked about at the start, which was what Murad all used to implement the BitVO algorithm on. So the Scan5 device itself just outputs binary edge maps. And as we can see, our algorithm actually are able to do most matches within this Scan5 dataset quite well. So in here, we managed to overcome some viewpoint changes, such as the rotation of the cupboard in this case. There's some, it also overcomes translation and scale within these images. And it also works with very sparse information. For example, these two images only have small squares and the rest are all black, but our algorithm still successfully managed to match them. And the last thing is also that our algorithm also managed to overcome some noise, where we could see that in this image, there are actually these light bulbs occurring here, whereas this image doesn't have, but our algorithm was still able to match these two images. So what do we conclude? Our algorithm was able to identify all unique loop closure sequences on the new college dataset and majority of the unique sequences in the city center dataset, with none of it being a false positive. Another interesting thing about our algorithm is that it was actually trained exclusively on binary edge maps of synthetically produced images. And when we actually tested it on this real life dataset, it was still able to successfully and reliably detect loop closures. So that's all for my presentation. Thank you and goodbye.